In 1808, John Dalton, a self-taught Quaker scientist from Cumberland, England, published a new system of chemical philosophy, a work that would transform chemistry from a collection of observations into a quantitative science. Dalton proposed that all matter is composed of tiny, indivisible particles called atoms, each element having its own unique type. This revolutionary idea, built on precise measurements of combining ratios, laid the foundation for modern chemistry and atomic physics. John Dalton was an English chemist, physicist, and meteorologist whose meticulous work laid the foundations of modern atomic theory. Born into a Quaker family in Eaglesfield, Cumberland, he received little formal education but taught himself mathematics, meteorology, and chemistry. He kept daily weather observations for over 57 years, more than 200,000 entries. Dalton discovered his own color blindness, formulated the law of partial pressures, and most importantly, proposed the first scientific atomic theory backed by quantitative experimental evidence. The concept of atoms dates back to ancient Greece. Leucippus and Democritus proposed that matter consisted of indivisible particles called atomos. However, these ideas were purely philosophical, lacking experimental evidence. For over 2 millennia, chemistry remained alchemical. Robert Boyle in 1661 defined elements as substances that cannot be broken down. Antoine Lavoisier in 1789 published the first modern list of elements and established the law of conservation of mass. Joseph Proust in 1797 formulated the law of definite proportions. Dalton synthesized these ideas into a coherent, testable atomic theory. Dalton's atomic theory, published in 1808, rests on 5 fundamental postulates that form the bedrock of modern chemistry. First, all matter is composed of extremely small, indivisible particles called atoms. Second, all atoms of a given element are identical in mass, size, and properties. Third, atoms cannot be subdivided, created, or destroyed in chemical reactions. Fourth, atoms of different elements combine in simple whole number ratios to form compounds. And fifth, in chemical reactions, atoms are rearranged, separated, or recombined, never changed into other atoms. Dalton's theory beautifully explained Lavoisier's law of conservation of mass, which states that in a chemical reaction, the total mass of reactants equals the total mass of products. If atoms are indestructible and merely rearranged during reactions, mass must remain constant. This principle, established by Antoine Lavoisier in 1789 using precise measurements with his balance, was the first quantitative law of chemistry. Dalton's atomic model provided the elegant mechanistic explanation: atoms are neither created nor destroyed, only reorganized. Joseph Louis Proust discovered in 1797 that a given chemical compound always contains its constituent elements in fixed proportion by mass, regardless of the source or preparation method. For example, water always contains 8 grams of oxygen for every 1 gram of hydrogen. Dalton's atomic theory provided the explanation. If water consists of fixed numbers of hydrogen and oxygen atoms, then the mass ratio must always be constant. This was powerful evidence that atoms combine in specific, unchanging ratios. Dalton's most brilliant insight was the law of multiple proportions. When 2 elements form more than one compound, the masses of one element that combine with a fixed mass of the other are in ratios of small whole numbers. For example, carbon and oxygen form both CO and CO2. For 12 grams of carbon, 16 grams of oxygen combine in CO and 32 grams in CO2. The oxygen ratio is 16 to 32, which simplifies to 1 to 2. This was definitive proof of discrete atomic particles. If atoms were continuous, any ratio would be possible. Dalton published the first table of relative atomic weights in 1803, containing 6 elements: hydrogen, oxygen, nitrogen, carbon, sulfur, and phosphorus. Taking hydrogen as the lightest element and assigning it a weight of 1, he calculated relative weights based on the mass ratios observed in chemical compounds. While many of his values were incorrect by modern standards, the methodology was revolutionary. This was the birth of quantitative atomic science, the first time anyone had assigned numerical weights to atoms. Before modern chemical notation, Dalton devised an ingenious system of circular symbols to represent atoms of different elements. Each element had a distinctive circle: hydrogen with a dot, oxygen an empty circle, nitrogen a circle with a vertical line, carbon a solid black circle, sulfur a cross, and phosphorus a dot in circle. Compounds were represented by placing the symbols side by side. While Berzelius's letter-based notation eventually replaced Dalton's system, his symbols were the first attempt to visually represent atomic composition. Published in 2 volumes in 1808 and 1810, A New System of Chemical Philosophy was Dalton's masterwork. The book systematically presented his atomic theory, a table of relative atomic weights, descriptions of chemical compounds using his symbolic notation, and detailed experimental data. Dalton classified compounds as binary, ternary, or quaternary based on the number of atoms. The book transformed chemistry from a descriptive science into a predictive, mathematical discipline. It remains one of the most influential scientific texts ever written. Dalton worked with remarkably simple apparatus: glass tubes, balances, and rudimentary pneumatic troughs for collecting gases. His experimental approach was based on measuring combining masses with painstaking care. Despite being described as a coarse experimenter, modern replications of Dalton's key experiments confirm his remarkable precision. He analyzed the composition of water, ammonia, carbon dioxide, and nitrogen oxides by decomposing compounds and measuring the masses of products. His laboratory notebooks reveal thousands of careful measurements. Despite its revolutionary impact, Dalton's theory had several key limitations. He incorrectly assumed water was HO, not H2O, leading to wrong atomic weights. His rule of greatest simplicity assumed the simplest possible formula when only one compound was known, which was an arbitrary guideline. Dalton also rejected Gay-Lussac's law of combining volumes and Avogadro's hypothesis. He could not explain isotopes, which were discovered in 1913, or subatomic particles like electrons, protons, and neutrons, which were discovered later. Dalton's original theory was refined through successive discoveries. In 1811, Avogadro proposed that equal volumes of gases contain equal numbers of molecules. Berzelius developed modern chemical notation and vastly improved atomic weight measurements. Mendeleev's periodic table in 1869 revealed that atomic weights follow a periodic pattern. J.J. Thomson discovered the electron in 1897, showing atoms are divisible. Rutherford discovered the nucleus in 1911. Chadwick found the neutron in 1932. Today, the Dalton is the official unit of atomic mass. Dalton's atomic theory transformed chemistry from alchemy into a modern science. For the first time, chemical phenomena could be explained, predicted, and quantified using atomic principles. The theory provided the foundation for stoichiometry, the calculation of reactants and products in chemical reactions, which remains central to chemistry today. It enabled the development of the periodic table, molecular biology, materials science, and nuclear physics. Every chemistry textbook today begins with his 5 postulates. Quiz question 1. According to Dalton's atomic theory, atoms of a given element A. can vary in mass and properties. B. are identical in mass, size, and properties. C. can be created during chemical reactions. Combine in variable, non-integer ratios. The correct answer is B. All atoms of a given element are identical in mass, size, and properties. This is Dalton's second postulate. It was essential for calculating relative atomic weights, because if atoms of the same element could vary in mass, you could not assign a unique atomic weight to each element. Quiz question 2. Which law states that a compound always contains the same elements in the same proportion by mass? A law of multiple proportions. B. Law of conservation of mass. C. Law of definite proportions. D. Avogadro's law. The correct answer is C. Proust's law of definite proportions from 1797 states that a given compound always contains its constituent elements in fixed proportion by mass. Water always has 8 grams of oxygen for every 1 gram of hydrogen, regardless of its source. Dalton's atomic theory explained this beautifully. If water molecules always contain 2 hydrogen atoms and 1 oxygen atom, the mass ratio must be constant. Quiz question 3. Carbon forms 2 oxides, CO with 12 grams carbon and 16 grams oxygen, and CO2 with 12 grams carbon and 32 grams oxygen. The oxygen mass ratio 16 to 32 equals 1 to 2 demonstrates which law? A. Law of conservation of mass. B. Law of multiple proportions. C. Law of definite proportions. D. Dalton's rule of simplicity. The correct answer is B. The law of multiple proportions shows that when 2 elements form multiple compounds, the masses of one element that combine with a fixed mass of the other are in small whole number ratios. The ratio 1 to 2 proves atoms are discrete particles that combine in fixed numbers. If atoms were continuous, any ratio would be possible. Quiz question 4. What was one major limitation of Dalton's original atomic theory? A. It could not explain the law of conservation of mass. It incorrectly assumed water was OO instead of H2O. C. It predicted the existence of isotopes. It could not explain chemical reactions. The correct answer is B. Dalton assumed water had the formula O based on his rule of greatest simplicity. The correct formula H2O was established later. This error led to incorrect relative atomic weights for oxygen. Dalton's rejection of Gay-Lussac's law of combining volumes was another limitation, as was his inability to explain isotopes and subatomic particles discovered later. Quiz question 5. The modern unit of atomic mass, the Dalton, is defined as a 1/10 of the mass of an oxygen atom. B. 1/12 of the mass of a carbon-12 atom. C. The mass of a hydrogen atom exactly. D. 1/16 of the mass of a nitrogen atom. The correct answer is B. 1 Dalton is defined as 1/12 of the mass of a neutral atom of carbon-12, approximately 1.66 times 10 to the minus 27 kilograms. The unit honors John Dalton's pioneering work in establishing relative atomic weights. This standard replaced earlier definitions based on hydrogen or oxygen, providing a consistent reference for all atomic mass measurements. Problem 1. Mass ratio in water. Water contains 2 hydrogen atoms with atomic mass 1 and 1 oxygen atom with atomic mass 16. Calculate the mass ratio of hydrogen to oxygen in water. Show that this ratio is constant, confirming the law of definite proportions. Step 1. Mass of hydrogen in one molecule equals 2 times 1 equals 2 atomic mass units. Step 2. Mass of oxygen in one molecule equals 1 times 16 equals 16 atomic mass units. Step 3. Total molecular mass equals 2 plus 16 equals 18 atomic mass units. Step 4. Mass ratio H2O equals 2 to 16, which simplifies to 1 to 8. Step 5. In 1 gram of hydrogen, we find 8 grams of oxygen. The ratio is invariant. Conclusion. The 1:8 mass ratio is constant for all water samples, proving Proust's law of definite proportions. Problem 2. Multiple proportions in nitrogen oxides. Nitrogen forms three different oxides: N2O with 28 grams nitrogen and 16 grams oxygen, NO with 14 grams nitrogen and 16 grams oxygen, and NO2 with 14 grams nitrogen and 32 grams oxygen. Show that these data obey the law of multiple proportions. Step 1. Fix nitrogen mass at 14 grams. N2O has 28 grams N, so for 14 grams N, oxygen equals 16 times 14 over 28 equals 8 grams. Step 2. For NO, 14 grams N combines with 16 grams O. Step 3. For NO2, 14 grams N combines with 32 grams O. Step 4. Oxygen masses for 14 grams N are 8, 16, and 32 grams. Step 5. Simplify the ratio. 8 to 16 to 32 equals 1 to 2 to 4. Simple whole numbers. Conclusion. The oxygen masses combine in the ratio 1 to 2 to 4, confirming discrete atomic particles. Problem 3. Relative atomic mass calculation. In methane, CH4, 12 grams of carbon combines with 4 grams of hydrogen. If hydrogen has an atomic mass of 1, calculate the relative atomic mass of carbon using the law of definite proportions. Step 1. In CH4, the formula shows 1 carbon atom and 4 hydrogen atoms. Step 2. Experimental ratio, mass of carbon over mass of hydrogen equals 12 over 4 equals 3. Step 3. Mass of carbon over mass of hydrogen equals atomic mass of carbon times 1 over atomic mass of hydrogen times 4. Step 4. Atomic mass of carbon over 4 equals 3. Step 5. Atomic mass of carbon equals 12 atomic mass units. Conclusion. Carbon's relative atomic mass is 12 mu, matching the modern value. Problem 4. Predicting compound formulas. Sulfur with atomic mass 32 and oxygen with atomic mass 16 form two compounds. Compound A has 32 grams sulfur and 32 grams oxygen. Compound B has 32 grams sulfur and 48 grams oxygen. Determine the empirical formulas of both compounds using Dalton's atomic theory. Step 1. Compound A, moles of sulfur equals 32 over 32 equals 1. Moles of oxygen equals 32 over 16 equals 2. Step 2. Compound A atom ratio S to O equals 1 to 2, which gives SO2. Step 3. Compound B, moles of sulfur equals 32 over 32 equals 1. Moles of oxygen equals 48 over 16 equals 3. Step 4. Compound B atom ratio S to O equals 1 to 3, which gives SO3. Step 5. Oxygen ratio, SO2 has 2 O atoms, SO3 has 3 O atoms, ratio 2 to 3. Conclusion. The two sulfur oxides SO2 and SO3 demonstrate the law of multiple proportions with an oxygen atom ratio of 2 to 3. Problem 5. Empirical formula from mass data. A compound contains 2.82 grams of nitrogen with atomic mass 14 and 6.44 grams of oxygen with atomic mass 16. Using Dalton's atomic theory, determine the empirical formula. Hint: find the mole ratio and simplify to the smallest whole numbers. Step 1. Moles of nitrogen equals 2.82 divided by 14 equals 0.201 moles. Step 2. Moles of oxygen equals 6.44 divided by 16 equals 0.403 moles. Step 3. Divide by the smallest. Nitrogen 0.201 divided by 0.201 equals 1. Oxygen 0.403 divided by 0.201 equals 2. Step 4. Atom ratio N to O equals 1 to 2. Step 5. Empirical formula equals NO2. Conclusion. The empirical formula is NO2, nitrogen dioxide. The mass data combined with atomic weights reveals the atomic composition. Key concepts and formulae summary. Dalton's atomic theory established the foundation of modern chemistry. Here are the essential concepts. Dalton's 5 postulates from 1808. All matter consists of indestructible atoms. Atoms of the same element are identical. Atoms of different elements differ. Atoms combine in simple whole number ratios, and chemical reactions rearrange atoms. The law of conservation of mass by Lavoisier states that total mass of reactants equals total mass of products. The law of definite proportions by Proust states that a compound always contains the same elements in the same proportion by mass. The law of multiple proportions by Dalton states that when two elements form multiple compounds, the masses combine in small whole number ratios. Dalton's relative atomic weights table from 1803 had hydrogen as 1, oxygen as 7, nitrogen as 5, carbon as 5, sulfur as 13, and phosphorus as 9. Modern values use carbon-12 as the standard. 1 Dalton equals 1/12 of the mass of a carbon-12 atom, approximately 1.66 times 10 to the minus 27 kilograms. The enduring legacy of Dalton's atomic theory. John Dalton's atomic theory stands as one of the most transformative ideas in the history of science. It shifted chemistry from qualitative description to quantitative prediction, established atoms as the fundamental units of matter, and provided a framework that has guided scientific discovery for over 2 centuries. Today, the Dalton unit honors his name in every chemistry laboratory. From the simplest stoichiometric calculation to the most complex quantum mechanical model of the atom, Dalton's insight that matter is composed of discrete, indestructible particles remains the bedrock of our understanding of the physical world.